I'm kidding. The only way that could be 0 is if x were an I number. So what does that mean my domain is then? All real. All real. And when we express, we can use a symbol, that's a symbol for all real numbers. If we're using interval notation, it is just negative infinity to positive infinity, right? It's the whole darn number line. So when we have x squared minus 4, that one we can solve. We factored it or square rooted, whatever you did, and said x can't be negative 2 or 2. This one isn't solvable, except as Josh said, it would have to be imaginary, right? See how it's going to be imaginary if we solve it? So there aren't any real number exclusions. So that means it can be everything. The domain is all real numbers. All right, everybody okay with that? All right, now we got a simple little section here. Vertical line test. Is it a function? What do you think about A? Yep. Passes the vertical line test. What about B? No. Everybody got it? Doesn't pass the vertical line test, right? C is an equation, not a picture. So we can think about this a couple of different ways. How are you thinking about it? What are you thinking about doing to answer this question? How would you figure it out on your own? What? Oh, so like solve it? Oh, I didn't write it down yet. Let me write it down. So it's y squared equals x plus 2. We can do that. Now, here's the first thing, guys, and we'll talk about this a little later on, but that is not graphable on your calculator in that form. Because what button do you hit when you're going to put an equation into graph? Y equals. It doesn't say y squared equals, it says y equals. So if I were going to graph this on my calculator, I would do exactly what you said. I take the square root of both sides. However, whenever I do that, what do I have to remember? Plus or minus. So you would be graphing the positive square root of x plus 2 and the negative square root of x plus 2. All right, just for fun, let's go ahead and put that in. They're both in. You're not looking where they intersect. You're just looking at what would this picture look like. If we put both halves of the problem together, what would it look like? You can just use a standard window. You don't need anything fancy. These two together make this. So what is this shape? It's a parabola, but it's not a normal parabola. It's a parabola that opens sideways, which means, is it a function? No. And your clue, kids, your clue was the fact that to graph it, you needed two separate equations, okay? If you can't put it in your calculator, then chances are it's not a function. Okay? So we know, because we've looked at lots of them, x squareds are parabolas that open up. Y squareds are also parabolas, but they're parabolas that open sideways. So that means not a function. What do you think about D? X equals 12 minus y. Do you think that's a function? Yes, it is. What shape would that be? It's just a line, right? And every line in the whole wide world is a function unless it happens to be vertical. And vertical ones won't want to have a y in them, so you'll be all set there. Okay, easy enough. Identify the type of discontinuity. review. A couple days ago, we talked about types of discontinuity. Anybody remember any of them? Continuity, being continuous, means you can draw it without lifting your pencil. So what kinds of things make us lift our pencil? We have holes, right? Have holes in the picture. We could have asymptotes in the picture. And then we have those weird ones that jump, right? Those are very strange. Those will have separate equations. We are basically looking at problem number A, 7A. I don't know where Caden is. This is unusual. Anybody have his number? Can you text him and just see what he's doing? Thank you, Jacob. He might get confused. Sometimes the Zoomers try to zoom in because they don't have the schedule figured out. All right. This problem is discontinuous, and you should know that by looking at it, because if I said to you, what's the domain? What's the domain? You would look at it and say, oh, it has a denominator. And whatever is in the denominator can't be 0, right? So the domain is everything up to 0 and everything after 0. This would be the domain. Does that make sense to you in terms of what we've already talked about? Now, the minute you tell me that x can't be something, that means that as I'm graphing the picture, whatever that looks like, when I get to 0, I'm going to have to stop. And then I'm going to have to start again, which means I'm automatically going to have to lift my pencil, right? So what I want to figure out is it's discontinuous, but I want to figure out, okay, is this going to be a case where I just have a hole, so I just skip over that point and continue on? Or is this going to be a case where I have an absolute break and I have a vertical asymptote? You can tell by seeing if you can remove the discontinuity. Can you remove the x from the problem? I mean, this x. You can't, because if you factor out an x on the top, it will cancel with the x on the bottom. Would you agree? So I can rewrite the problem as x squared plus 1. Now, what does that mean graphically? We're not ready to graph yet, but just stay with me. Let me show you what that means graphically. If I graph this right here, this new equation, it would be a parabola moved up 1. So it would look like this. If I graphed that, but that was not the problem. This was the problem. And you'll say, but Ms. Ford, they're the same thing. Almost. They're the same thing, except, can I put x into this equation? Sure I can. I get 1. Can I, or I mean x, 0. Can I put 0 into this equation? Sure I can. I get 1. Can I put 0 into this equation? No, that's the discontinuity. So the point 0, 1 is a hole in the picture. If you can remove the discontinuity, it's graphed as a whole. So when the question says, identify the type of discontinuity, this is removable, and there is a hole at the point 0, 1. Caution, if you type this into your calculator, it is not going to show you the hole. Okay? So you kind of have to know that on your own. Removable discontinuity is one that you can remove from the problem, and it shows up graphically as a whole. Jacob?
So if you decide to get rid of an
you are physically graphing it, you will always have a hole at 0, 1. Your calculator won't show that. It can't do holes. Okay? So you got to know that. That's a removable discontinuity. Now look at the next problem. What's the issue there? X can't be 2. So for this problem, X can't be 2. So your domain, if you were going to write it out, would be negative infinity to 2 and 2 to infinity. So definitely not continuous, because you can graph, but as soon as you get to 2, you have to stop and start over again. Can that discontinuity be canceled out? How? What are you going to cancel it with? If you're going to cancel it out, you would have to have something like x plus 3, x minus 2, over x minus 4, x minus 2. That would cancel. But can I cancel anything here? No, you're stuck with that one. That is a non-removable discontinuity. And a non-removable discontinuity is an absolute break in the picture. It is a vertical asymptote. So this problem is going to have a vertical asymptote at x equals 2. In other words, the picture isn't going to be like this one, where we drew it and just had that one little skip there. It's not going to look like that. This is going to be a chunk of picture over here and an entirely unconnected chunk of picture over here. This is a complete break in the problem. Removable discontinuities, if you can cancel them out, you're going to graph them as holes. Non-removable discontinuities, you're going to graph as vertical asymptotes. They don't cancel out. All right, even, odd, or neither. Okay, this goes back to yesterday a little bit. How do we tell if something's an even function? It has to have y-axis symmetry. And what, there comes Katie. And what is our test for y-axis symmetry? Who remembers? Think of me as the y-axis. Going from this side to this side, what changes? X, it's negative over here, positive over here. So we change the sign on X to go back and forth across the y-axis. So when I look at problem number A, y equal, I would write it as y equals x to the 4th. If I change the sign on x, does that simplify to the same thing as the original? If you do a negative 4 times, doesn't it disappear? So this would be the same as x to the 4th. So that has symmetry about the y-axis, which means it definitely is even. Let's check it for odd. What's the symmetry for odd? Or what's the test for odd? The origin, which means we change the sign on both. Is that going to simplify to the original? No. So it is even but not odd. What about this guy? See if you can figure out if this is an even, odd, or neither. It's definitely possible to be neither. See if you can figure that out. do you think? You think it's even? Because if you change the sign on x, don't you get the same equation back again? So this is an even function. It is not odd. All right. Next. Try not to get bored, guys. This is fun stuff. All right, so let's check for even first. So y equals 2 negative x cubed minus 3 negative x. Now, what happens when we have an odd number of negatives? It stays negative, right? So this would be negative 2x cubed, and this would be plus 3x. That is not the same as the original, is it? But now when I do odd, I'll change the y also. Is that one going to simplify to be the original? Yeah, it is. So this is an example. C is an example of an odd function. So A and B were even, but C is odd. What do you think about D?
Would it be odd?
What do you think, class? Jacob is surmising that D is odd. The equation is y equals 1 over x. If you make them both negative, is that going to be the same as the original? Yeah, he's right. It's an odd function. Very good. And what about E? Please don't feel that you have to show a ton of work. If you can think about the problem, because I'm looking at it and I'm thinking, okay, if I put a negative x into the first term, it won't matter because it's getting squared. But isn't it going to change the middle term? So I don't think it's even, because a negative x is going to change it. What if I change both signs? You think you're going to be okay if you do that? I don't think so. Because if I change both signs, I'm going to have negative y equals negative x squared plus 0.03 negative x plus 5. So if we simplify that, and again, you don't have to show every single step. Show as much work as you need. You're going to have negative y equals negative x squared minus 0.03x plus 5. What happens when I divide by this negative? I get x squared plus 0.03x minus 5. Is that the same as the original? No. So that's an example of a function that is not even or odd. Does anyone have a question about that? Cosine is even, sine is odd. We'll learn about that very shortly. All right, so now we're doing all the asymptotes. Woo, we're doing great. All the asymptotes. I remember today's lunch period. I remember that. We'll go to lunch as soon as we're done with some of these asymptotes. Just think, the more we get done now, the less we have to do later. All right, so y equals x over x plus 1. We have vertical asymptotes, and we have horizontal asymptotes. There are also something called slant asymptotes. We're not going to talk about them right now, but we will. All right, here we go. Here we go. A minute ago, we had a problem that had a vertical asymptote in it. Do you remember, where did that come from? How did we get that thing? I called it a non-removable discontinuity. Where did it come come from? Grace, what? Okay, so my asymptote was like x equals 2 or something. Where did that number come from? Where was I looking to get that number? Denominator, right? Because that was where I was discontinuous. So looking at this problem, what can you tell me about the domain? X cannot be -1, right? Cannot be's are vertical asymptotes. So when you say to me absolutely, positively, can't fix it, x can't be -1, then your vertical asymptote is x equals -1. Remember, vertical asymptotes intersect the x-axis, so they are x equals lines. If you intersect the x-axis, you're at x equals. These are going to be y equals lines because they cross the y-axis. All right, so my horizontal asymptote is y equals. This is a little bit trickier. So I'm not sure how you would even write this down, but just think for a second, listen. Horizontal asymptotes are actually limits. They are what happens to the problem as x gets really, really big. I mean really big, like zillions big, okay? So I want you to think about it. In this fraction, if x got really, really big, the top would get really, really big, right? I mean, x is getting really big. The bottom would also be getting big, right? Would you agree? Now, are they ever going to match? No, because the bottom's always going to be one bigger. But as you go farther and farther and farther out, don't they get closer and closer together? So basically, eventually, they're never going to equal 1, but they're going to get real close to 1 because they're almost the same. To get the horizontal asymptote, we simply look at the x part of the problem. We ignore the number, we ignore the 1, because as x gets to be a billion, 1 doesn't matter. And so our limit is x over x, so your asymptote is y equals 1. Y equals x over x, and x over x is 1. Let's do the next one. Where is the vertical asymptote in the next one? Yep, your vertical asymptote is x equals -3. Make sure when you write down your asymptotes that you're writing equations. They are equations. Don't just say -3, say x equals -3. And why is that the vertical asymptote? Because that's what x cannot be, right? Can't be -3. You get a 0. Now, what's our horizontal this time? Remember, we're only looking at the x parts. So now we have 2x over x, which reduces to 2. So your horizontal asymptote is y equals 2. Your picture, when you graph this thing, your picture is going to be split into pieces based on these asymptotes. Here's x equals -3, and here's y equals 2. So you're going to have a chunk of picture over here, probably something that looks like that, and a chunk of picture over here. I might have those switched. It might go this way, but it doesn't matter. It's going to have some kind of a shape like that. 2 separate pieces. Right, what about C? What are the asymptotes in C?
Is the vertical asymptote 0?
Well, the vertical asymptote would be 0 if x cannot be 0. Can x be 0 in this problem? Yeah. Are there any cannot be's for this problem? No, where do cannot be's happen? When the denominator is 0? Well, wait, do I have a denominator? No. So I do not have, so for problem C, which, by the way, what shape is that? That's a trusty little parabola. There are no vertical asymptotes. actually there are no horizontal asymptotes. Because gang, if you don't have a fraction, are you going to be able to find a vertical asymptote by comparing the top and the bottom x's? No fraction, no asymptotes. All right, what about D? What are you thinking? Well, I'm old, I do this for a living, and I've done millions of these, so when somebody says to me, find the vertical asymptote, the first thing I think is, what can x not be? Okay, so x can't be I, right? Something I. Okay, am I worried about i's right now? Not in function land, I'm not. So if you tell me the only thing x can't be is I, then what does that mean about what x can be? Everything. Do I have a vertical asymptote? No. What are you doing, Jesus? Nobody back there's cuter than me. Okay. Horizontal asymptote. This one is tricky. Jacob?
The case that he's waiting to be
Oh.
accepted.
Oh, no, he's in.
Oh, okay.
He's in. Yeah. Thank you. I let him in a while ago.
Oh,
Yeah.
no.
That's okay. You're not supposed to be on your phone, so thank you for not being on your phone every minute. How about a horizontal asymptote now?
Is there none?
Actually, there is one, and this is a little bit tricky. So let me come back to the problem that I had over here, something like this. And we said we were looking right here, right, at the x's. Now, if I do that over here, I've got a 1x squared in the bottom of the problem. How many x squareds are in the top of the problem? 0. So I'm going to physically write 0x squared up there on the top. Because when I do horizontal asymptotes, my job is to compare the x's on the bottom and the x's on the top. Right? But when I do that comparison, what I didn't tell you is you have to compare the same power. So you can't compare x's to x squareds. You got to do x squareds to x squareds. So I have no x squareds to compare. But I do have a fraction. What is 0 over 1? 0. So your horizontal asymptote is 0. I hate memorizing stuff. A little FYI, when the power on the bottom is bigger, when you have more x's on the bottom than you have on the top, it'll always be 0. The horizontal asymptote will always be 0 if you have more x's on the bottom than you have on the top. All right, 3 more and then we're going to lunch, okay? So we've got x squared minus 1 over x squared plus 1. I need vertical and horizontal asymptotes. Anybody have a thought?
No vertical.
No verticals. I love it. And Jacob, why are there no vertical asymptotes?
Because if it's an imaginary number, then it can be anything.
There is nothing real, no real number that you could put in here and get 0. That will never be 0. And if you don't have an excluded value, I cannot be, then you do not have an asymptote, a vertical asymptote. What about a horizontal asymptote in this problem? It is 1. Y equals 1. And why is it y equals 1? Look right here, guys. When you compare your top x's with your bottom x's, you get 1x squared over 1x squared, which makes 1.
So anytime it's a parabola, will the
minus one down here, let's say they were switched. That would not change the horizontal asymptote, but now there are two vertical asymptotes in this problem because x cannot be 1 and x cannot be negative 1. So vertical asymptotes are all about what makes the denominator 0. And if that's a minus, there are two numbers that make it 0, 1 and negative 1. So it would have two vertical asymptotes. When you make it a plus, nothing makes that 0, right? All right, what about F? F's tricky. I'll just warn you right now, F is tricky.
Is there no horizontal asymptote?
There is no horizontal asymptote. And Jacob, why do you think that? You are exactly right.
Because there's no x squared at the bottom, and we need to compare the same powers of x squared. But since there isn't any x squared at the bottom, that means there's no horizontal asymptote.
We got to be careful because when we had no x squared on top, we still had an asymptote. What happens, Jacob, is I need an x squared on the bottom, so I can go ahead and put one down there. But what happens when I put 1x squared over 0x squared? What's 1 over 0? Undefined. That's why there's none. FYI, when you have more x's on top than you do on the bottom, you'll never have a horizontal asymptote. So when you have more on the bottom, it's going to be 0. When you have more on the top, it's going to be none. Now, I am not saying that there isn't what we call an end behavior asymptote. There will be a slant asymptote in this problem, but it will not be horizontal. It will be something like this, and we'll talk about that later. So horizontal asymptote for this problem, none. Whenever the power on top is bigger, that's going to happen. None. All right, what about a vertical asymptote?
Negative 3.
That is what you are so tempted to say, but that's what makes this tricky. Look at your numerator. What can we do with the numerator?
Cancel it out.
We can factor it, can't we? So if we factor the numerator, we get x plus 3, x minus 3. And what do you notice? You can cancel out the x plus 3. So ultimately, aren't you just left with the equation y equals x minus 3? And when you graph that, y equals x minus 3, isn't that just a nice little line, just like that? But in the beginning, could x be negative 3? No. So that means wherever x is negative 3, which would be like this point right here, you're going to have a hole. That is a removable discontinuity. There are no vertical asymptotes because what you thought was going to be an asymptote actually got canceled out. And when it cancels out, then it becomes a removable discontinuity, which is not an asymptote, it is a hole. This line looked like that, nobody has a problem with that. But you have a discontinuity that you canceled out at negative 3. If I plug negative 3 into this equation, I get negative 6. That's that point right there. And that point has to be open because it doesn't fit the original equation. Everything else there's fine, but not that one particular point. So on that problem, would you just add, there's no asymptotes, but you have a hole at negative 3, negative 6. Quick recap, we got one more problem to go. Vertical asymptotes are cannot be's, right? what x cannot be ever. Horizontal asymptotes come from comparing your x's in the top and the bottom of a fraction. Where do holes come from? Canceling something out of the denominator. That produces a hole. So let's put it all together in this last problem. I think we might see it all here. We're not quite ready to sketch this one yet, but certainly find its discontinuities. So, seriously, you write that down, you immediately think I have to do what? Factor it. You gotta factor it. So how does the top factor? Minus 4 plus 4, perfect. How about the bottom?
X minus 1, x minus 4.
Minus 1, minus 4, is that okay with everybody? What's the very first thing your beady little eyes notice? We can cancel. Uh-oh. The minute we cancel means we're gonna have a hole, right? What is the x value of that hole? 4. 4. Because that is the one you canceled out, right? You would have had an asymptote at 4, but it canceled out. Okay, when I cancel, I'll be left with x plus 4 over x minus 1, right? That's what I'm left with. You guys know how I'm going to get the y coordinate here? Where am I going to get the y coordinate for that hole? No, it won't be the horizontal asymptote. We still have to do that, though. We won't be finding that. Exactly. So I'm just going to put 4 right in here. Kids, you can't put 4 in the original. It won't work because it gives you 0 down here. But you can put 4 in here, right? What do we get if we put 4 in this equation right here? 8 over 3. So your hole is at 4 8/3. This is a tougher graph, so I'm not going to do the graph. But what that would look like is at 4 8/3, whatever this thing is, it's going to have a hole right there. Now, looking at the new equation now that you have simplified, does it have any vertical asymptotes? 1. X equals 1. You have a vertical asymptote at x equals 1 because there is no way you can simplify any further. X cannot be 1. Period. Do you have a horizontal asymptote? It is also at 1. Now notice, if you would have done the horizontal in the beginning, would you still have gotten 1? Yeah, because you look at the highest power, right? So you could have done that at the beginning. I waited to do it at the end. So that problem has a whole bunch of stuff. All right, ready to do lunch? Let me get our sign-out sheet here. Today is the 18th. All right, so let's go ahead and sign out. Jason, I need you back at 12:30, okay? Why were you late? Why were you so late? Did you forget what time? Well, not at the beginning of the period, you weren't. At 11:15?
Yes, ma'am.
You didn't show up at all. You didn't show up at all. Sorry about that. All right.
Technology's weird.
That's why I had Jacob text you, because you didn't show up.
Yeah, I messaged him back.
Okay.
The second I got it.
Well, we're going to lunch at 12:30, okay?
All right.
I bet we're back at 12:30.
All right, I'll be there.
Okay. guys, or whatever, we got it up here. Oh, I'm gonna stop this video too. We don't need to videotape lunch, do we?